Hello there, welcome to the second lecture of module 3. In this lecture we will know about the probability distribution of random variable. In the last lecture we have seen that definition and concept of this random variable. Now this concept and definition of this random variable generally useful in this probability theory through its probability distribution. We have to know that over the specific range, over the specified range of one particular random variable, how its probabilities are distributed, and this is what we will discuss in today's class. So our outline for today's presentation is, first we will discuss about the general description of the probability distribution, how this probability distribution, what it is all about, how we can define the probability distribution for a random variable. Basically there are two different types of random variable we consider. One is that probability, one is that discrete random variable, and then the continuous random variable. This probability mass function will be discussed for this which is for discrete random variable, and probability density function which is for this continuous random variable, and their cumulative distributions is also known as the cumulative distribution function. So this will be discussed, and for all these things we will see some example problems as well. Now probability distribution of a random variable, it says probability distribution of a random variable is a function that provides a complete description of all possible values that the random variable can take, along with their probabilities over the range of minimum and maximum possible values in a statistical sense of that random variable. So here the meaning is that a random variable, in the last class we have seen that this random variable can take some specific value over the for one particular random experiment. The specified that sample space can be correspondence to the real line through this random variable, which is nothing but the random variable, and that random variable is generally a functional correspondence to the real line some number. So it can take some numbers, and that is generally having certain range, and over this range, if we just see it here, over this range of these variables, how suppose that one random variable, this is your the axis for this random variable, and if we just say this side is your probability, then if I say that this is the range of this random variable, now thing is that here how this for each region, if it is continuous, then for some region how this probability is distributed over it for this entire range of this random variable. In the context of this probability distribution, this is known as the support of the random variable, and over this, if it is a discrete random variable, then for the specific values the the probability will be specified. On the other hand, if it is continuous, then it will be distributed as a function over this entire support. Thus, so now again the another point here is the minimum and maximum possible values. This minimum and maximum possible values, in obviously this is in the statistical sense. What is meant is that maybe a random sampling, if we take for any random variable, if we just see for one observation that the maximum of that one or minimum of that sample need not be the maximum or minimum of that random variable. So that can have some other values, that is what is meant by the statistical sense, and this will be obviously discussed again in details when we are going to some specific distribution. For the time being, what is important is that a random variable, it is having a specified range, and this probability distribution gives us the distribution of the probability specified for all possible values that the random variable can take. Now, as I was just mentioning that it can so there are two different concept. One is for this discrete random variable, another one is for the continuous random variable. As we discussed in the last class, that discrete random variable here means that it can take some specific value over the range of this random variable. It cannot take all possible values, even though traditionally or in most of the cases this discrete random variable takes the integer value, but that is only the concept. It can take any specific value, not only integers, but it takes only that specific value. So, that is a discrete random variable. On the other hand, the continuous random variable can take any value over the entire support of that of the distribution or entire range of that random variable. So, first we will discuss the probability distribution. We will discuss with respect to this discrete random variable. It states that probability distribution of a discrete random variable specifies the probability of each possible value of the random variable. So, you can see here there is one random variable x which can take the values 0, 1, 2 and so on up to 9. So, at each and every possible values that the random variable can take, the probability is defined there. So, now there is nothing in between two integers, because this random variable take the integer values only. So, in between two integer values, say for example between this 1 and between this 2, there is nothing is specified here. So, this space is entirely is not specified by this distribution. Okay. So, here what we can say that this particular at a particular point of this random variable for a particular specific value, this one can be treated as a mass. So, this is a concentrated at a particular point. So, this is why, so this can be treated as a concentrated mass. That is why it states that being probabilities, the distribution function of the discrete random variable are concentrated as a mass for a particular value, and that is why it is generally known as the probability mass function and abbreviated as probability PMF. So, what is meant here, that as there is nothing specified in between two specific values of the random variable. So, what is specified for a specific value of the random variable can be treated as a mass of probability, that can be treated as a mass. So, that is why this kind of distribution we know it's known as the probability mass function, abbreviated as PMF. On the other hand, as for the continuous random variable, this is not the case. So, this is specified over a region. So, on the other hand, the probability distribution of a continuous random variable, specified continuous distribution of the probability over the entire feasible range of the random variable. So, if the random variable is continuous, then that random variable is specified over a region, over a range of So, the distribution function should be specified in terms of obviously in terms of a function over the entire range. And in contrast to the discrete random variable, the probability is distributed over the entire range of that random variable, and at a particular value the magnitude of the distribution function can be treated as density. Thus, the distribution function of continuous random variable is generally known as probability density function and abbreviated as lowercase of PDF. So, this point, that is its concept of the density, I will just explain it here. As I was telling, that if this is the entire support of the, so now what I am discussing, this is in case of the continuous random variable. Okay. So, for this continuous random variable, if I say that okay fine, this distribution is specified, distribution is shown by this. So, for what it first of all what is showing that for some region this probability is lower than with compared to some other region. For example, this region here it is more and this region here it is less. Now, thing is that if I in this case if I just mention that a specific value of that random variable x, so this is that specific value. Now, what does this implies? Is this implies the probability? Now, if I just draw the same thing for the discrete, then what I have seen just now, what we have seen just now, for a specific value of this random variable, the probability what is specified, what is concentrated here is nothing but the probability. In between there is nothing is specified. So, in between this region nothing is specified, but whatever is specified that is nothing but the probability. Now, for this one, if I just say for a specific value, what is this height meant? This is very important to know that this height is not the probability. Then where is the probability here? So, here the probability means that, so I have to specify a small region around this. So, some small region, then what we are getting? We are getting some area, and that area is nothing but your probability is showing here. So, at a particular point, if I consider here, this height is nothing but we can treat that this as a density, the density of the probability here. Once you are multiplying the density for a normal physical sense, if you multiply that density with its mass, then you will get its weight. So, similarly here this is nothing but the density. If you multiply over a certain range, then you will get the area, and that area nothing but your probability. So, that is why for this distribution, for the continuous random variable, this distribution is the probability density function. So, this is why the word density comes here. So, once again if we just read it, that in contrast to the discrete random variable, the probability is distributed over the entire range of this random variable, and at a particular value the magnitude of the distribution function can be treated as density. Thus, the distribution function is known as this probability density function. This will be more clear when we are talking about that one of the axiom that we have seen in the earlier classes, that the total probability obviously should be equals to 1. So, this will be clear in a minute. So here what we are trying to say is that why this word density. So, next we will first start with this probability mass function PMF, which is for this we just now have seen, this is for the discrete random variable. So, whenever we mention that PMF, this is for the discrete random variable. The probability mass function PMF is the probability distribution of a discrete random variable, say x. Generally this is denoted by Pxx. So, here this notation is important. This P is the lowercase. Now, this P is lowercase, this subscript x is denoting the random variable. So, this function is for which random variable? This is shown as the uppercase letter as a subscript to this one, and this one is lowercase, which is nothing but a specific value of this one. This we also discussed in the context of some other distribution in the last lecture. That, so this one, this lowercase is the specific value of the random variable which is shown here x, and this small p, this is nothing but for this probability mass function. Now, it indicates the probability of the value x equal to that specific value x taken by the random variable x. So, there are some properties for this random variable, just what we are just indicating in this last slide, is that the first property is that for each and every value whatever this random variable can take should be greater than equal to 0. So, this probability can never be negative. So, this is a non-negative number, and the summation of all these probabilities. Now, this x is defined over some specific values of this one, that is, so there are some specific values of x where this probability is defined. Now, if we add up for all this possible value, all the possible values of this x, the probability of the all possible values of x, if we add up, then it should end up to 1. So, these two are the properties of this probability mass function. Now, some notes on this PMF. These are obvious, but still it is important to mention here that in a particular case, it is, if it is certain that the outcome is only C. So, for a random variable, I am saying that there is only one outcome and that outcome is certain and that outcome is C. Then what is this Pxc? The distribution function is nothing but Pxc, which implies the probability of x is equals to C. This is the only outcome that is feasible, and this is a certain outcome. So, this will obviously come up. So, this is equals to, so this should entirely be equal to 1 to satisfy all these properties of this PMF. On the other hand, if there are some mutually exclusive outcome for one random variable, that is say x1, x2 up to xn. Now, if we just say that these values, these specific values of a random variable x are mutually exclusive, then if we want to calculate what is the probability of either of these mutually exclusive values that the random variable can take, should be equal to the summation of their individual probabilities. So, this is obvious in case of a throwing a dice, and there are 6 possible outcomes, and if we say that all the outcomes are equally feasible, equally possible, and if I just take that number 1 to number 4, then the probability, the total probability that the random variable will take either 1 or 2 or 3 or 4 will be equal to the summation of the probability of getting 1 plus summation of the probability plus probability of getting 2 plus probability of getting 3 and plus probability of getting 4. So, we know that this 1 to 4, these events are mutually exclusive. So, this can be, so these properties we explained earlier in the context of this random variable. Here we are explaining in the context of the specific value that a discrete random variable can take. So, one small example we will take on this probability mass function. This is taken from the Kotegura and Rose book. The number of floods recorded per year at a gauging station in Italy are given in this table. Find the probability mass function and plot it. So, now here for this 1939 to 1972, there are, so number of floods are noted here. So, 0 floods. So, this table is this, the 0 flood has occurred in 0 years. So, and 1 flood has occurred in 2 years, 2 flood has occurred in 6 years, 3 floods can occur in 7 years. So, in this way, the total number, so 9 floods in a year occurred for 0 occurrence. So, if we just add up the total years, this 34 should match with the whatever the data that is available to us. Now, we have to define the PMF for this one. So, this kind of problem, the first thing that we should think that what is the random variable that we are talking about. So, this is one of the, even though this is sometimes for this kind of problem this is quite obvious, but this is important to know that what is the random variable here. So, occurring the flood is not the random variable. I repeat, the occurring of a flood event is not the random variable here, rather the number of floods in a year, that is the random variable. So, while solving this problem, first of all what we will do, we will first define that what is the random variable that we are mentioning. So, let x, that is the random variable, denote the number of occurrence of flood. Thus, for the given data, the probabilities of the different number of the floods can be obtained as follows. So, Px equals to 0 number. If we take this number 0, that is the number of flood occurring 0 flood, no flood in a year should be equals to 0, because from this table we see there is no such a year where the number of flood is 0. Similarly, if we want to know the what is the probability that x equals to 1, that means from this sample data obviously. So, x equals to 1. So, that means there are 2 such occurrences out of 34 years. So, 2 by 34 should be the probability for that specific value of the random variable, that is x equals to 1. Similar, so this is what the probability of x equals to 1 is equals to 2 by 34. Similarly, for x equals to 2, 6 by 34, x equals to 3, 7 by 34, and in so on, we are going and getting all these probability values. Now, similarly, we are assuming one thing, that as so number of 9 floods in a year, this is occurring 0 and all, we just got the summation this one. So, there is no other higher numbers of flood. If I just take 10, 11, there are also number of occurrence in a year. For 10 floods in a year 0, 11 floods in a year 0. So, to complete the definition of this PMF, then Px x equals to 0 for all x greater than 9. Now, simply we have to plot this one as a mass function for these specific values only, nothing in between 1 and 2, because that is not specified, which is obvious for the discrete random variable. So, this is the plot. So, for the 0, the probability is 0, and obviously for 9 probability is 0, for all higher values this is also 0. For 1, these are the probabilities whatever the value we got here. So, we are getting these masses. Now, obviously do not confuse that this, what is the meaning of this line. Basically, this line, this solid line has no meaning, just as a geometric reference that this point refers to this number 1. Otherwise, a single dot at this point should be sufficient to display the probability mass function. Okay. Now, we can, from this probability mass function, we got the probability mass function for the data that we have. Now, several things can be answered from this one. Now, if it is asked that what is the probability that number of flood is greater than equal to 5. So, if I say that number of floods greater than equal to 5, then obviously I have to just add up these values. If I add up these values for the probability for 5, 6, 7, 8 and 9, then I will get what is the probability that the number of flood in a year is greater than 5. So, this is the utility of this PMF, that all of this kind of answer we will get from this probability mass function, and this we will again see while we are discussing the cumulative distribution function. So, this is for the discrete, and there are some standard example, there are some standard probability mass function that is for the discrete random variable. This is the binomial distribution. We will discuss all these distribution again in detail in the successive lectures, but for the timing we can just know their names. The binomial distribution, that means there are binomial distribution means there are this is a Bernoulli trial where there are 2 possible outcome, and one we just tell it as success, and the success for each trial is predefined, is known. So, now the number of success out of n successive such trials, so that is the number. So, that number is a random variable, and that random variable follows this binomial distribution. Similarly, if there are more than two outcome, then for the how many success we are getting in a set of say 1 to k, and all these success rates are known, then the vector, that is that x1, x2, x3 up to xk will follow the multinomial distribution. Similarly, there are different definition for this negative binomial distribution, geometric distribution, hypergeometric distribution, Poisson distribution. These are all example of this, the distribution of discrete random variable, which will be covered in the successive lectures. Now, we will go to the distribution function of the continuous random variable. So, this continuous random variable, when we are taking, we call it as the probability density function. Why it is density, just we discuss now. So, a probability density function, abbreviated as lowercase of PDF, is the probability distribution of a continuous random variable. Do not confuse about this abbreviated form. These are the abbreviation will be followed for this lecture, but in some standard reference book you may get some other notation, but here we are to mean that probability density function we generally abbreviated as lowercase of PDF, just to differentiate it from this cumulative distribution function, where the D stands for the distribution, here this D stands for the density. So, so this PDF is the probability distribution of a continuous random variable, and generally it is denoted by this fxx, which we discussed last time also, that this is the random variable which is the uppercase letter, and this is the specific value of the random variable which is shown as the lowercase of this of the letter. So, here again you can see that this is the distribution function defined over this one. So, this is the total range of this random variable that it can take, and obviously here the density is more and here the density is less. Now, we will see that there are, obviously it is not that any function that I will take and I can tell that this is the probability density function. That is not the case. There are certain properties, there are certain conditions should be followed to make a particular function to be a probability density function, and those conditions are this. So, there are two conditions for a valid PDF. The PDF is a continuous non-negative function for all possible values of x. So, fxx for all x should be greater than equal to 0. This is basically coming from the first axiom of the probability. So, in this graph, so everything that is coming above this towards the positive y axis, and the total area bounded by the curve and the x axis is equals to 1. So, that this shaded area, what you see here, this shaded area below this graph above this axis should be equals to 1. So, this is basically mean that if I take the entire range of this random variable, then this is becoming a certain event. So, any possible value will take here. So, this is the entire set of this sample space, and which is equals to 1. So, the total probability of this entire range should be equals to 1. So, here we have just written the minus infinity to plus infinity of the x. So, take care about this full one. So, obviously this is reducing to this the lower limit and the upper limit of this one, because the rest of the places this random variable is defined to be 0. So, this is the second property. So, if any function that pass through these two condition, then that condition can be a valid PDF. Now, this is one important concept what was just discussed while discussing the density, that when the PDF is graphically portrayed, the area under the curve between two limits x1 and x2, such that say x2 is greater than x1, gives the probability that the random variable x lies in the interval of x1 to x2. So, this probability that this random variable will be in between x2 and x1. So, this is graphically nothing but, as we are telling that each and every point here, this implies the density for that particular value. So, if I want to know what is the probability that this random variable be within this limit, which this is nothing but this hashed area over this in this graph. So, this area will how will we get it as this? So, if this will integrate from this x1 to x2, this integration, and this will obviously be less than equals to 1, because the we know that this total area is equals to 1. So, now again if we just see this in integral form, then it looks like this. So, the integration here is, so in integration what we have seen here is that fx x dx okay, from x1 to x2. Now, what we are just discussing here, that this is the density here. Basically what we are doing here for this graph, so we are taking a small, so dx is this small strip here, dx is the small strip here. So, this is your dx, and this fx is gives you that particular value for this area. So if we multiply these two, which is nothing but the probability you are getting over the area dx, and this area you are just basically adding up from this x1 to up to x2. So that's why you are getting the total area below this two limits from x1 to x2, and that is nothing but which is gives you the probability, and this probability is obviously from this x1 to x2. Now one thing here again is important, so far as the continuous random variable, so I just specify it, so far as the continuous random variable is concerned, basically this probability that x1 less than equal to, so this sign I am just stressing the point, this equal to sign, having this equal to sign or not having this equal to sign doesn't mean anything, because ultimately for a particular specific value the probability is 0, as this range for this particular value over which the probability we are defining is 0. So this equality sign, inclusion of this equality sign or not in inclusion of this one doesn't change the total probability. So what we can express is that less than equals to x2 is equals to probability of x1 less than x less than equals to x2, and whatever the combination possible is that x1 less than equals to x less than x2 equals to probability x1 less than x less than x2. So all these 4 cases the probability is same as long as this random variable is continuous. This is one important concept here while we are calculating the probability from the PDF for a continuous random variable. Now we will take one small example, mathematical example rather, to discuss about this PDF, how to satisfy their properties. Suppose that the function fx x is equals to is alpha x power 5, and which is defined over the zone for this x value from 0 to 1, and it is 0 elsewhere. Now to be this is a valid PDF, what is the value of alpha that we have to determine, and what is the probability of x, say that is greater than equal to 0.5. So if we want to know this first one, that is the what is the value of this alpha, then we know that the property that this should be from this entire range of this random variable, that is 0 to 1 in this case, that this function should be equals to 1. Now if we do this one, then this will be alpha this x power 6 by 6, which is equals to your 1. This is alpha, so it is 0 to 1, 1 by 6 minus 0 equals to 1, where the alpha is equals to 6. This value we got. So now what we will see that this so what we got, that fx of this x equals to your 6 x power 5 over the range this x 1 and equals to 0 elsewhere. So now the second thing is that what is the probability that x is greater than equal to 0.5. This we can express that, you know, that 1 minus probability of x less than or less than equals to, you know, that for this continuous random variable these two are same, is equals to 0.5 less than equals to. So 1 minus this we can do that from 0 to 0.5 6 x power 5 dx, which is 1 minus 6, x minus 6 by 6, we can just write here 0 to 0.5. So, which is equals to 1 minus say 0.5 power 6. So, you can we can calculate this probability with the help of this. The two things we want to discuss here now. One is that just to get this x is greater than equals to 0.5, what we can do is that we can just do the integration from 0.5 to 1, because this is the range 0.5 to 1. We can do this integration directly to this function and we can get the probability, and answer obviously will be the same. What instead of that also what we can do, we know that the total probability is equals to 1, say 1 minus the rest of this part from this means here 0 to 0.5, what is the area that we have deducted to get this probability. Basically this relates its link to the CDF, because we will just see in a minute that what is a CDF. So, from the CDF we can directly calculate what is its probability, and that probability value we can put in this place instead of. So, that is why it is replaced in terms of this one, just for one illustration purpose, which can be linked to the CDF that we are going to discuss in a minute. But so far as this particular problem is concerned, we can also calculate the integration from 0.5 to 1 to get this this particular probability answer. So, second, there are, as we have given some standard example for this PMF, probability mass function, which is for the discrete random variable. There are some example of some standard PDF as well, which is for the continuous random variable, and most popular distribution is a normal or Gaussian distribution. This normal distribution is a continuous probability distribution function with parameters mu and sigma square. This is known as variance, and its probability density function, that is PDF, is expressed as this one. This is 1 by square root of 2 pi sigma square multiplied by exponential of x minus mu whole square divided by 2 sigma square. Now, this mu and sigma is known as the parameter of the distribution. Now, this if you change, keeping the basic shape of this probability same, these things are implies different properties of this particular distribution. Before that, what is important, so this is not the complete definition of this PDF until and unless you say what is its support. So, here the support is minus infinity to plus infinity. So, in absence of this one, basically no function is a valid PDF. So, whenever you are defining some PDF, this support must be specified for that function. For example, here, so this one, once you are getting this alpha 3 by 1000, then the PDF is, this is equals to 3x square by 1000 for x 0 to 10 and equals to 0 elsewhere. So, this support is very important. You know that if you do not specify this support, then whether this the total area below the curve is equals to 1 or not, that cannot be tested. So, here similarly for this normal distribution, this support is minus infinity to plus infinity. So, here are some example of this normal distribution is shown here. This is basically a bell shaped curve, and depending on these two parameter, this can be changed. So, generally this mu is the location parameter. I repeat, this mu is the location parameter where this distribution, where is the center of this center. Now, I use this word center very crudely. We will discuss all these things maybe in the next class, but this is the location. Now, you see here there are 3 different graphs are shown here, all are normal distribution, but for the different parameter value. So, this blue one, the mu is 0. So, its location parameter is 0, and the black one is again the mu equals to 0. So, you can see that this point both are the maximum density is located at this 0. So, here again the sigma is the spread, the variance is the spread about that mean. So, this is 1, and for the second one it is 1.5. So here you can see that at the spread for the black one is more and for the blue one is less. For the green one, here the mu equals to 2. So you can see that, so this is shifted and the center here again is at 2 and sigma is 0.75, which is lower than this the first one, this blue one. So these are called, this mu and sigma are called some parameter of this distribution, and this normal. So normal distribution is symmetric, that you can see it is bell shaped, and skewness. So all these things, the skewness, mean, variance, these things will be discussed in the next class. So, and again the normal distribution also in detail will be discussed in subsequent classes. What we are just telling here is that this is the over the entire support. Here the support is from the minus infinity to plus infinity. One function is defined here, and if you do this one here, you cannot do this integration. This is not a closed form integration. The numerical integration has proven that this integration from minus infinity to plus infinity is equals to 1. So the area below this curve is equals to 1, and this is known as this normal or Gaussian distribution. Similarly, another important distribution known as the exponential distribution. This exponential distribution is the probability distribution function with parameter lambda, and its probability density function is expressed as the fx equals to lambda e power lambda x for x greater than 0. Again you see this support is defined here is greater than equal to 0, and this lambda is known as the parameter of this distribution, and it is 0 otherwise. So for the entire support from the minus infinity to plus infinity, this is there. So this is basically defined in the defined for the positive x axis. So these are again some example of this exponential distribution for different values of lambda. So this blue one is showing the lambda is equals to 1. So now this lambda, this parameter is generally having some relationship with their different, as I just discussed, the mean and all. This will be discussed in the next class, but for the time being this lambda is the parameter for this distribution. So and the difference between this one difference from this, so this is only one parameter is there, as against that normal distribution where there are two parameters are there. So this is a single parameter distribution function. This lambda, if we change this lambda, you can see if the lambda equals to 1, this blue curve, the green curve is for the lambda equals to 0.5, and this black one is for lambda equals to 0.25, and these are all defined from this 0 to plus infinity. Now this integration is very easy, you can just test for these values. If you do the integration from 0 to 1, then we will get that the total area below this curve above this x axis will be equals to 1. Third one, these are basically this is whatever the distribution that we are mentioning here, both for this PMF and for this PDF. This is not the, this need not be the complete list, only some examples we are just showing here. You can some more distribution will be covered in the successive classes as well, and here just we are giving some example which are generally very important and mostly used almost all the field and more importantly all the fields in the civil engineering. So the third example that we are giving is this gamma distribution. Again this distribution is a two parameter distribution. The parameters are alpha and beta. So this is the form of this distribution. This is the one parameter alpha, and this is another parameter beta, and this is the gamma function. Gamma function again is defined by this this integration form, and if this alpha is positive integer, then this form can be proven. So this distribution, again this is basically specified for the positive x axis. For the negative side, this is 0, this is 0. Now if you see, there is one interesting point here. If you just see that if you change this alpha to be equals to 1, then this is nothing but, so alpha equals to 1, gamma alpha is equals to, so 0 factorial, which is equals to 1, and alpha equals to 1, so 1 by beta, so this is x power 0, so this is 1 by beta e power x minus x by beta. Now if the 1 by beta is lambda, then this is nothing but lambda e power minus lambda x. So this is again, so if I put this alpha equals to 1, this is becoming a exponential distribution. So here you can see, if we just change this parameter, then this shape changes, and the first is the blue one, the where the alpha equals to 1 and beta equals to 2. As this alpha equals to 1, this is nothing but the exponential distribution. For the green, it is alpha equals to 4 and beta equals to 2, and for the black one, alpha equals to 2 and beta equals to 1. So these are again different gamma. This is the gamma distribution with different parameter values, different combination of the parameters. Now the another important thing in this class that we will discuss is the cumulative distribution function. Now to say it specifically, what we have seen now for the discrete as well as for the continuous distribution, we have seen that for what is the probability for a specific value in case of the discrete, and for what is the density of the distribution, how it is distributed over the range. Now this cumulative distribution function, so for the earlier that PMF you can get the probability directly, for the PDF you cannot get the probability directly, you have to do the integration over the range to get that one. Now CDF is the cumulative distribution function. So basically we are just going on adding up the probabilities starting from the left extreme or the lower extreme of the support to the higher extreme of the support. So if we just go on adding up the probabilities, the resulting graph will be the cumulative distribution function. So for a discrete or for a continuous random variable, the cumulative distribution function, abbreviated as CDF, uppercase CDF, this D stands for the distribution here, and denoted by this fxx. This is the random variable and this is the specific value of the random variable, is the non-exceedance probability of the x, and its range is between 0 to 1. So as I was just discussing that we are just going on accumulating this thing from the lower extreme. From the lower extreme it is 0 and the upper extreme it will be 1 obviously. So this fx, as it is stated here, is nothing but the probability for a specific value x, the probability of the x less than equal to x. So whatever the lower value of that specific value of this x, the total probability up to that point is nothing but this cumulative distribution function. Sometimes CDF for the discrete random variable is denoted as Pxx. Just this P is now again the uppercase letter, and you have seen that PMA, probability mass function, we use this letter as a lowercase p. So this notation will be followed for this course as well. Now to again just what we are just telling now, if we just show it here. So now this is your the probability distribution function that we are doing. Now what we are trying to say now, to calculate this probability, we have seen that we have to go for this one, go for this range in integration of this range. Instead of that, for this for the CDF, what is meant is that we will, so for this one, for this specific value, I will calculate this, what is this total area, and total area will be put here. So up from here where the range basically is starting, so this is starting from this 0. Now we are just going on adding up these values, and I will just go on adding. So this value means nothing but the total area up to this point, and in this way we will go on adding, and once we are reaching here, we know the total area below. Just now we discussed the total area below this graph for a valid PDF is equals to 1. So if we just go on accumulating up to this point, obviously I will reach to the point where this is equals to 1. So obviously this axis which I drawn it earlier for this PDF need not be the same for this axis. I can just use one more axis system where it starts from this 0 and this is ending up to this 1. And as we are going on adding up these things, obviously this will never come down. It for some time, if it can go horizontal, but it can never come down, as this is an cumulative function, as the quantities are getting added to this the earlier value. So if this is understood, all this concept for this CDF will be clear. Again, if I get this graph, which is CDF, then for a specific value of this random variable, if I want to know what is the probability that x is less, so if this one is x, then what is the probability that random variable less than equals to that specific value, is nothing but is straightforward, we will get it from here. So this will be nothing but this particular probability what we are getting it here. So now we will go one after another their probabilities. Sometimes, so this is none. Now if we see the properties of this CDF, this fx, that is which is denoted as this CDF, or the px in case of the discrete random variable, what is just now as told, is bounded by 0 to 1. So this is obvious, as we are starting from this left extreme of this support and going up to the right extreme. So it will obviously start from 0 and it will go up to 1. Secondly, this fx or this px is a monotonic function which increases for the increasing values of x. So this is bounded by this 0 to 1. Again, this is monotonic function which increases with this x. This is also can be cleared from this graph. That is, as we are adding up the areas, as we are adding up some quantity to the previous value, obviously this function will always increase with the increasing values of the x. So these two are the properties of the CDF. So now we will just take a small thing for this one, just to discuss for this discrete random variable. This is one important thing, that is, for a discrete random variable CDF, that is px, is obtained by summing over the values of this PMF. For a discrete random variable, the CDF pxx is the sum of the probabilities of all possible values of x that are less than or equal to the argument of this x. So this is equals to, for this all values of this x which is less than x should be added up. If we take the example of the throwing a dice, and we know that for this all this out, there are 6 equally probable outcomes are there for all the probabilities. The probability is 1 by 6 if these are equally probable. Now if we want to know what is the CDF for this one, this will be the starting point of our next lecture, and we will see that this is very important to know, and where it can touch and where it cannot touch. This looks like a step function, and from the next class onwards we will start a detailed description of this one. So so in this class what we have seen is that we have seen the distribution of a particular random variable, and this random variable can be discrete, can be continuous, and in the next class also we will see one example if there are kind of mixed random variable, that also we covered in this that we told in the last class. So here we will see that how to handle this issue, that is the PDF, CDF for this one, for the mixed random variable as well we will see. So we have first discussed this PMF, probability mass function, which is for the discrete, PDF, lowercase pdf, which is probability density function, which is for the continuous, and then we have seen how to calculate, how to get the CDF, cumulative distribution function, from PMF or from the CDF. The concept we have seen, and for the discrete one, how to get actual representation of this PMF will be discussed in the next class, along with some of the examples taken from the civil engineering problems. Thank you.